Hi, I would like to welcome you all for my presentation today. I'm Dr. Chamila Bacon from the University of Manchester. First of all, I would like to thank the organizers of the International Conference on Fluid Flow and Thermal Science for inviting me to deliver this keynote speech in this virtual conference. So it is my pleasure to deliver the keynote speech today, which is titled Soft Sensing and Fuzzylogic Based Control for Industrial Processes. If you want to contact me in relating to any matters relating to the presentation or my research, please contact me via chamil.abekon@manchester.ac.uk. And also you can find more information about my research in University Profile and Google Scholar and ResearchGate. Before we start, some of you might wonder the background for my presentation today. So this is a picture showing one of the wonderful places on earth, which is the ancient Sigiriya kingdom in Sri Lanka. It is very famous in the world for its working water fountain, which are even more than 2000 years old. So this might be a wonderful place many of you would like to visit. So with that, I would like to start my presentation by giving a brief introduction about my workplace. I'm working at the University of Manchester, as I said. So this is one of the oldest buildings that we have, and this building includes the Manchester Museum as well. So University of Manchester is the only university in the UK which owns a museum as well. Right. Also here you will see some of the nice buildings in the South campus of the University of Manchester, and some of you may recognize this is the National Graphene Institute of the United Kingdom. And this is the place where recent Nobel Prize winners for graphene are currently working at. Okay, and then I'm attached to the Department of Materials at the University of Manchester, and mainly working with Aerospace Research Institute and also with the Northwest Composite Center. And this is me at the University of Manchester website. So you'll find the most of my details here if you would like to have more information. So please drop me an email if you would like to. Right, for today's talk, I would like to deliver this talk based on two parts. The part one on sub-sensors. So mainly, what is a sub-sensor, why sub-sensors are important in process monitoring, and how to design a sub-sensor. I'm going to just look at a case study based on the polymer extrusion process, and then conclusions and some future works relating to that area. And then for the second part, would like to talk about fuzzy logic based control, and designing of a fuzzy logic based control. Again, a case study mainly based on very briefly about polymer extrusion process and some of the conclusion of the paper work. Okay, so then I would like to start the first part, and then at the end of the presentation, so I'll be available to take any questions if you have any questions relating to anything that I discussed today. Okay, a sub sensor. The sub sensor can have a number of different meanings. Actually, it is mostly relating to the software-based sensor. So these sensors could based on one measurement, or maybe even dozen of measurements, or maybe even hundreds of measurements. So we can process these measurements together. The idea here is we try to process these signals, and then we are going to calculate a new quantity or new parameter which cannot normally be measured in practice. Okay, so hence a term, the sub sensor is based on the words software and sensor. So it is the shortened to call it as sub sensor. Right, if you ask me the definition of a sub sensor, how to define the term sub sensor, so here I have written the definition. A sub sensor is a technique of estimating process parameters in various applications when a hardware sensor is unavailable or unsuitable for making direct measurements. So sub-sensors are really important. So to measure or to predict some process parameters when we cannot use the physical sensors due to some constraints in the process or the environment, and also when if there is no any physical sensor available for some parameter measurement, so then we can use a sub-sensor. Sometimes you will find this is known as a virtual sensor or hybrid sensor or inferential sensor. So all of these terms are for the software-based sensors. Right. So the most of these inferential sensors are used in real-time process monitoring, modeling and control, and also sometimes in fault detection and estimation, the process diagnostics. So mostly in continuous processes which operate in 24/7. So of course, these processes are running continuously. So then it is very important to have the measurements as much as you can actually in several locations to observe the process functionality, to observe the process quality, and therefore we need to have some advanced measurements. So then sub sensors can play an important role in this type of occasions, right? So if you look at the current industry, so the substances are already being used in the current industry. So that is the important thing. So this is mainly being used in chemical industry, polymerization reactors, distillation columns, cement kilns, in food processing industry and paper pulp production industry, mainly to estimate product quality parameters. Okay, and then these substances can be a continuous source of the information for process functionality or product quality, as I mentioned before. And these can be used for process optimization and also for energy optimization and for several other purposes as well. And also, if we can have more measurements, which are really useful, so then this can be helpful for process control purposes as well. Right. So then in general, if you look at the substances, we can categorize them into two types. So model driven is the one type. So these are based on first principle models. You hope you know how to develop first principle models based on physics. And the other type of substances could be data driven. So these are mainly based on actual data measured from the processing plants. So then you can collect the information in the offline modeling or maybe inline modeling, or we call online modeling. So we can use data-driven substances based on the actual the data collected from a plant. Okay, so then of these two types, model-driven substances, so they are based on first principle models, are mostly used in steady state processes to analyze the physical and chemical background of the process. Okay, so while the data-driven substances can represent the process dynamics quite well compared to model-driven substances, because the data-driven substances are based on real process data instead of physical or first principle models. So therefore, the data-driven substances are popular, but so it is quite challenging to develop sometimes. Okay, and there are a number of challenges or issues or limitations are attached to the development of substances, both type actually, model driven or either the data driven. So there could be some limitations in developing these substances or virtual sensors. Right. So if I'm going so in this talk I'm going to focus on data driven substances. Okay, so I'm going to look at how we can design a substance in briefly. Okay, so it has number, we can just the design process can be classified into a few different stages. So the first stage is the data collection process. So here I'm going to look at the required the parts or require the essential the task, and also maybe optional task in developing a subsensor. The first one is a data collection. So if you look at a data-driven subsensor, we should have a very good set of data. So then we can use the data actioning devices and set of sensors, and then the process investigation, the procedures to collect a good set of the data. So when we are going to design system identification experiments to collect the data set, so you should know which parameters you're going to predict, and then so therefore which sensors you should be using. And then here some things to be considered: the accuracy or the quality of sensing devices and data acquisition units. So it is a quite well-known factor. So sometimes if you know how, so you should have some idea about how quickly your process is changing. So when you select some sensor, so then that sensor should be updating quick enough to capture all the process dynamics. So therefore, selecting process the sensors and also data acquisition devices should be compatible with the speed of your process. Otherwise, so then these devices might not be able to capture all the process dynamics fast enough. So therefore, the sensor that you're going to develop might not be able to represent your process properly. So therefore, the data collection stage, you should know which parameters you want to record and how fast you want to record them, and then so which parameters you're going to predict at the end using a virtual sensor or sub-sensor. Then the data processing is important. So there are a number of processing techniques available. So statistical methods can be used. There are so many, you can name them. There are a number of strategies you can use. And then some things to be considered: the quality of the data set is really important. So there could be missing data, noise, outliers, and these things. Once you just record the data, so you should check your data set for all possible issues like this. And then if you find any outliers or noise, you can just filter out those these the unnecessary or unrelated the data points to avoid any possible confusions or possible inaccuracies that can be introduced to a sub sensor. And then the third stage comes to the model selection. So then model selection means, yeah, so you have to recognize, okay, so I'm going to predict this parameter using a sub sensor, and then the which parameters should be included as inputs to predict this the required parameter. And also you have to get the structure of the model. So you could say I'm going to predict the parameter X as a function of PQR. So then you should know what these PQR and then how you're going to measure them. So you should select, then you have to define the, once you have the structure of your model that can be used in sub sensor, then you have to select a modeling technique. So you can use some fast recursive algorithm or the ARX or whatever the modeling technique that you're going to use to develop the model using a software like MATLAB or whatever the software, it is your choice. So depending on your choice, the accuracy and the easiness of developing the models could depend. Okay, so it's important to select the structure of the model, and then you select the proper modeling technique. So also you have to think about the computational power that you're going to spend for developing these models. If you try to run this model online, so then that is also one concern. So to check, you have to check whether you have enough computational facilities for that, and the sensors are good enough to do those those online modeling as well. So then, of course, for any model, once you develop any model, so then you have to just validate it. And throughout this process, the expert knowledge is really important, as you can imagine. Then the accuracy of the models are really important. So to ensure this accuracy, so structure of the model is important. For example, let's say you have a process, the output is dependent upon 5-6 variables, but if you decide to only choose 2 variables to develop your models, although the process is depending upon several other variables, your accuracy of your model may not be good enough. So therefore, you have to decide what are the key process parameters to influence the output. So therefore, you have to include all of these parameters into your model to get good accuracy. So the model validation or the model testing and training should be done proper ways. So that is also important to make sure that your model is doing well. So then once you have data collection, data processing, and then you develop the models, and then you validate the model properly, and then you can implement the sub sensor. So ideally, sub sensor will have a set of inputs based on some real-time measurements from your process, and then we have the interface between the interface or the algorithm, your model is a soft platform, and then so once you provide the input to a soft platform, so it will predict the parameter that you need. This can be done, you can develop this model offline, or most probably if it is a continuous process, it would be better to develop online modeling. So then you provide the input to your model, and then it automatically predicts the output based on the algorithm or the model that you have in the soft platform. So then once you implement the sub sensor, it's important to think about the interface and inputs, and also data acquisition devices and sensors that you're going to use. So those are important things to be considered. And then the one of the other important parameters is when you collect the data set, so you should make sure to run your process within the whole operating envelope. So if you don't run the process within your whole operating envelope, so what will happen now? So let's say you record the data of your process at the first stage between 0 to 50 RPM, but if your process is normally running above 50 RPM, so let's say, so use a sub sensor to predict some parameter. So when you run the process about 50 RPM here, so then your sub sensor might not be able to predict the required parameter accurate enough, because you have not collected the data within that range. So therefore, when you collect the data set to develop a sub sensor, it is important to run or get good data set covering whole operating window of your process. That is also really important. So then you can avoid so unseen operating limits. Okay, so if your process is running from 0 to 200 RPM, you better run the process between those the two limits. So to collect the data to cover whole operating range, that's important. And also the maintenance is another thing. So with the time, let's say you have a substance developed and then it is predicting some particular parameter in the process. So with the time, so this model can just have some the offsets or drifts. So therefore, in the long run, you have to redevelop the models or adapt them to be compatible with the changes in the process. Okay, so then it is really important. So and also the other thing is, if you have a substance, it is highly advisable that you try to record or just see these signals in real time to check whether your sense is giving the sensible measurements. So that will be a good idea to see these the predicted parameters on a display to get some good indication that it is working fine. Okay, so then as I said, expert knowledge is really important throughout whole process. So then the advantages, there are several advantages of using sub-sensors. So we can just implement using the existing hardware platforms, and also it's easy to update because it's a soft platform, so then you can update the model without any problem. If you have new models developed. And then it's important, as I said, we can use them when hardware sensors are not suitable or they are not available. And the real-time estimations can be done without any time delays. So if you, let's say you are taking the measurements, so then if your sensor is far away, and then it could introduce some delays between the interface or the control panel and the sensor. But sub-sensors can be implemented by considering those time delays. And then possible easiness and simplicity of maintenance, but I would say it could be complicated depending on your process and how complex it is. Right, and also it could be low cost. Again, it's something you have to consider. So if, let's say you want to use a thermal imager to predict some or to analyze some parameter, it could cost maybe $3,000, but you might design a sub sensor to get the same thing using some reasonably good sensors available in the market for $1,000. So therefore, it's your choice which one is more suitable to be used. And then challenges and limitations. Obviously, the expert knowledge is one key thing. So for example, so the person who is going to develop a sub sensor should have the knowledge on the process itself. Let's say you're going to develop a sub sensor for polymer extrusion process. The person who is developing the sub sensor should have a good idea about the polymer extrusion process itself, how it works, and then what are the parameters, and then what are the possible instabilities in the process. At the same time, that person should have good knowledge on data processing, modeling, and then developing algorithms. So then therefore, the expert knowledge is really important in developing sub sensors. And also the performance of a sub sensor depends on the training and validation data sets. So therefore, the quality of the data is important. Sometimes it might be difficult to get a good set of data using some available cheap sensors. And the data-driven sub sensors might be specific for a given condition. For example, let's say you run the process for one particular diogeometry and then for some certain set of speeds. So then if you develop a sub sensor based on those set of data, so that could be good only enough for within that range. If you run the process outside that range, so then your sub sensor might not capture those dynamics. So therefore, it is important to look at the whole operating window when you develop sub sensors. And the other thing, maybe one of the solutions would be, so you can develop some generalized models to cover the overall processing behaviors if you can. Right. So from here onward, I'm going to look at a kind of brief study or the case study of developing a dye melt temperature predictive sub sensor for polymer extrusion process. A dye melt temperature profile predictive sub sensor for polymer extrusion process. Okay, if you don't know the extruder, so this is an extruder, a basic arrangement, how it works. So then here we can just feed in some solid materials, solid polymers, and then it will drive through the extruder screw, and then while absorbing the heat. So polymers will run through while absorbing the heat. The heat can be provided externally, and also the heat can be generated internally via friction and viscous dissipation. So at the end, so we should have a molten polymer which is thermally homogeneous. So if you say this is a circular cross section, so throughout the cross section we should have a certain temperature. Let's say we set the temperature to be 200. We would like to have it melt. Throughout the cross section we would like to have a temperature to be 200 degrees, and then this melt can be pressed into the die. to get the desired shape. So if we don't get the high quality melt, which is thermally homogeneous, so then there could be problems in the product. Okay, so I'm not going to discuss more about the extrusion process. So we are going to look at the melt quality at this end. Okay, right. Then what is the motivation for this work? So the while ago we were looking at the thermal, the efficiency and specific energy consumption of extrusion processes. So then we realized that thermal fluctuations, I mean, that is the thermal fluctuation across the melt flow cross section. Let's say it's a 38 millimeter die. So then if you look at the cross section in radial direction, so we want to look at how, how big the fluctuations are when you look at the output. And then we realize that these thermal fluctuations are increasing. I'm going to show you some experimental information. So these are just increasing with the speed, and the specific energy consumption also decreasing with the speed. So you can see that. So these the two variables, thermal quality and specific energy consumption, are having opposite correlations. So therefore, most of the processes are running at conservative rate at operating point somewhere here. So we can't run the process somewhere here which is having a good energy efficiency. Okay, if you run the process over here, then you can see thermal fluctuations are quite high. So then what we need is, so we want to move this operating point into somewhere here. So which is really difficult. So then if you want to run the process in this way, so then we should understand the correlations between energy and thermal parameters. So that is a requirement. So that is why we wanted to look at how we can quantify the thermal fluctuations in the polymer extrusion process. So so then we wanted to know how to quantify thermal fluctuations. So then if you look at the process here, I'll show you the short video. So so this is how you will find the output of an extruder. So you can see it's a really highly sulfur, and then it's a highly viscous melt. So if you're going to place a sensor across this to measure the temperature cross section, it's going to be really challenging. So the sensor should be really robust. Okay, so it's not easy to make a measurement using the physical sensor across that output. So therefore, so this is the output of the extruder, and then so we wanted to check the temperature variation across this cross section. Okay, so then those are the motivation. So we wanted to develop a model to predict the temperature profile at this location or at this location. So what we did then, so we wanted to measure it experimentally. So then we checked the available sensors. I'll come to that in a minute. So then these are the measurements that we made, some experimental measurements. So these are the measurements made for the one of the dies, which is 38 millimeter in diameter at different speeds. Okay, you could see at 10 RPM. So we set the temperature to be 200 degrees at at this location at the die. So then, but you know what will happen at 10 RPM now? So at the middle of the melt flow is going up to 218. Okay, so middle of the flow is 218, while this is going to now 200. But as the screw speed goes up, you could see 10, 30, 50, and 70 and 90 RPM. So now at 90 RPM, the maximum in the middle is 240, and then the lowest somewhere in somewhere close to the die wall, it is around 192. So then the variations are as big as 50 degrees. So then that is a big issue. Okay, so then we wanted to develop a model to predict this melt temperature profile, and then by having that model, so we wanted to develop a soft sensor. Okay, so then that is what our target was in this study. So ideally, so what we need is, if you set 200 degrees here, we need to have 200 degrees across the melt flow cross section, but we can't get that. This is actual results. Okay, so then we looked at the available sensors in industry. So conventional thermocouples, infrared sensors, ultrasonic probes, autotraversing probe, thermocouple mesh. This is not industrial, it's a research setting, pros and techniques. So only few of them can be used to measure temperature profile. Okay, and also some of them are non-invasive, so disturbing the flow. And accuracy is also another factor, and response time is also another factor. By looking at all of these, we decided that we could use the thermocouple mesh technique. But unfortunately, it is not an industrially viable technique yet. Okay, and this is another indication of the comparison of different temperature sensors. So here you'd see now, so this is all of these measurements related to thermocouple mesh at different radial locations across the melt flow. So you could see they capture really high dynamics or high variations of melt temperature. while the thermocouple mesh is capturing really huge temperature fluctuations, you can see the infrared sensor, this signal here, it captures some dynamics, this red color signal. Okay, it can follow the thermocouple mesh, but it cannot pick up the magnitudes of the variations. And this is insulated, non-insulated thermocouple is the green one. So you could see it shows really flat temperature profile. So then it's not good enough. So this non-insulated thermocouple, even worse maybe. So it's just is the green one, sorry, the blue one. So they are just indicating really stable melt temperature, but actual temperature fluctuations are really huge. So these infrared sensors, wall-mounted thermocouple shown in green, red, and then blue are the most commonly used in industry. So therefore, the industry is getting the stable signals, but actual thermal fluctuations, you can see they are really huge, especially in high speeds. Okay, so then we developed some the experimental setup. So this is the what we call the thermocouple mesh that we developed. We place that across the melt flow. So this is a mesh. So we can okay, I'll show you in the next the slide here. In here, you'll find we can have place number of several junctions across the melt flow. Each and every junction will develop a voltage. So that voltage can be converted to a temperature value using the algorithm. So therefore, we can get the temperature profile across the melt flow. I'm not going to get into details about this technique. So this is how we measured this thermocouple measured the melt temperature profile across the melt flow using this thermocouple mesh technique. Okay, but this is really fragile. You can see tiny wires here, so they can be easily broken, and also it is disturbing the melt flow, and also add some shear heating effect. So therefore, this is not viable in industry. Okay, so then this is another indication of how the temperature varies with the screw speed, 10 RPM, 30, 50, and 90. You can see flatness of the temperature profile is decreasing. So that means the fluctuations are getting higher and higher. So this is the effect of set temperatures. This is 200 degrees set temperature at die. So this is 220 degrees set temperature. So you could see the fluctuations at different locations are dependent upon the set temperature as well. So it's over here. Okay, so this is the zero in the middle of the die. So this is somewhere close to the die wall. So these fluctuations are huge here, but the lowest variation in the middle. So it's really complicated the thermal behavior. So then what we wanted to have now, so then we wanted to predict this because this is not possible to measure in industry. So we can't use a thermocouple mesh in industry. So we wanted to have some replacement of the thermocouple mesh sensor with a SOP sensor. So we wanted to have a thermocouple mesh sensor to be replaced with the SOP sensor because we can't use the thermocouple mesh in industry. So then what we did, we planned some system identification experiments covering the whole range of the extruder. So up to 0 to 90 RPM at number of different temperature settings. So this data set is more than 3 hours continuously. So we collected the training and testing data sets, and then after that we trained a model. So then we selected the model structure, which I was mentioning in the previous slides. So we just recognized that the key parameters which decide in the melt temperature of extrusion process is the screw speed, and then the radial position across the die, and also set temperatures of the barrel. So these are the key parameters. Apart from these parameters, we have other material parameters like density and viscosity. But so at this stage, so these are the main parameters. We did not add these material parameters. So this can be added later. So this is the structure of the model to predict the melt temperature profile that we decided at first stage. Screw speed, melt temperature across at different radial locations is a function of screw speed, radial position, set temperatures of the barrel. Okay, so then we consider all of these die and all the zones to be in the same temperature. That is what we did in the experiments as well. We use the same temperature across all of these zones. Then once we develop this the structure, and then we just use a linear interparameter modeling structure or modeling technique to develop the models. Okay, so I'm not going to discuss much on this, and then you can find the more information in these publications, and then we have published already about these techniques. So this is a good technique to develop polynomial models. And then, so we develop the models. Okay, so this is a comparison between experimental and model estimated, model estimated melt temperature profiles at different process settings. So this side set temperature increasing A, B, C, and this is screw speed 10, 50, 90 RPM. you can see that the red line is the estimated one, black line is the experimental measured lines using thermocouple mesh. So then our model is pretty good. So then we can replace the thermocouple mesh with our model. So here you could see we don't have a black line, so we don't have experimental measurements because the sensor was broken. As I said, the thermocouple mesh is really fragile, and then it can be broken at some situations. So therefore, that is why it is not compatible with the industrial settings yet. So then now we have a model to develop to replace the thermocouple mesh, and then now we want to extend this to be a sub-sensor. So these are the kind of models that we develop. So okay, the TP model is the model, the main model that we're going to use in the sub-sensor to predict the melt temperature profile. So I'll mention what this is. TIR model is a model to predict the temperature measured by an infrared sensor. I'll explain why we need this model as well. So in the sub-sensor, so we needed to have two main models, TP model and TIR model. So TP model is the model to predict the melt temperature at different locations. So then TIR model is a model to predict the melt temperature measured by an infrared sensor. So we're going to use this as a feedback model. Okay, so this is the structure now. So in our sub-sensor, so this is the extruder, and then we have process inputs. So we're going to measure them. So those are the inputs to our models. Screw speed, set temperatures, and then here in the extruder we just use an infrared sensor to make actual measurements as well at the end of the die. Okay, so then now we just use our TP model to predict the melt temperature profile. So once we have a melt temperature profile across the die melt flow, so then we can get the average or the average melt temperature profile. So we just feed that in to the TIR model. Okay, the TIR model is a model to predict the infrared temperature measurement that we make here as well. So what we are trying to do now, we have actual infrared measurements, and also we have predicted infrared measurements. So this measurement is based on the TP model as well. So then we can get the error between measured and estimated. So then if there's no error, that means we can assume that TP model is doing well and then the measurement is really good. Okay, if there's an error in the TIR measured and TIR predicted, so that error can feed back to this. So then it will correct the temperature, the prediction of the temperature prediction model. Okay, so then you can find more information in some of our publications in IEEE transaction in industrial electronics and control engineering practice. So this is for temperature profile prediction model, and this is for the sub-sensor. Okay, so then these are some simulation results. So you can see this, the predicted is the blue, and actually measured values are in this dotted line in red. So you can see some kind of mismatches, of course. So, but please look at this value here. So you can see that value is really high. It's 250, 250. If you look at the fully scale reading, then this prediction error is really less than 5% even. Okay, so then our sub-sensor is good in predicting the melt temperature profile at different radial locations. So this is at the middle of the melt flow, and this reading is at 3 millimeters away from the middle. 8 millimeters away from the middle. So this is a circular die, and then this is 16.5 millimeters away from the die. Okay, so it's good enough. So then our substance is working fine. So this is about the error signal. So predicted infrared and measured infrared. So it's quite pretty good. So that you can see the time here. So we testing this sensor for now more than 2 hours. It's working quite fine. So this is the error here. TIR error is quite small. Okay, so based on that, so this is the first sub-sensing approach proposed for die melt temperature profile prediction in polymer extrusion. So it is showing a very good the results at simulation and testing stages. Okay, so then what we want to do now? So this is a very good sensor, and then over 129 minutes period, it gave less than plus or minus 5 degrees for full scale reading. So that's quite pretty good, and therefore, so then this sense is really quite good if we can develop this into the industrial level. So then for the future works, what we are going to look at here. So we're going to implement this substance as a plug and play device. So then once we have the inputs measured, more importantly, these inputs are really readily measurable parameters. Screw speed and set temperatures are the key parameters that you can measure without any problem, without disturbing the process in industry. So therefore, we can use those parameters and input them into our model. So then it can automatically or easily predict the melt temperature profile across the melt flow, although we cannot measure it in using a physical sensor. So our next target is to implement this sub sensor as a plug and play device. And also, we wanted to extend this sub sensing technique not only to polymer extrusion and also for the other polymer processes as well. Okay, so that is all about the soft sensing, the task that I want to discuss. So therefore, the soft sensing is really important, especially extrusion process is a black box. So it's difficult to place sensors inside the flow without distracting the flow. So therefore, soft sensors are important. That is why we wanted to try. So then now we have a sensor to predict the melt temperature profile, although we cannot use actual sensor to measure the melt temperature profile across the die melt output. Right, so then with that, I would like to go to the Fuzzylogic based control without wasting much time. So here I'm going to give a very brief idea about Fuzzylogic based control and how we can use this in industrial process control. This has been used for a long time actually. So Fuzzylogic was proposed in 1960s by Professor L.A. Siddha, and then it has been used in and then emerged in 1970s, and then now it is being used in everywhere. It's really popular technique in process control. So why the Fuzzylogic is important compared to the conventional techniques? So then we can implement a controller with multiple rules without integrating into a single analytical law. That is important. Okay, and also, so we can develop some simple linguistic rules, although I say simple linguistic rule may be complicated again based on the process, so with a basic knowledge. And then we don't need to define exact the numerical boundaries with Fuzzylogic controllers. So then that is also a good thing. So they can work based on qualitative information. Possibly it could have low installation cost as well. Okay, so if you look at the Fuzzylogic controller, so hopefully most of you have some idea about this, but if you don't know, so I would like to give a brief idea. So this is a basic arrangement of a Fuzzylogic based controller. It has the four main elements. Okay, so these are fuzzy rules. So you have to develop these rules based on based on your process. So then these are the identity you're going to represent the process. So then these rules could be different from process to process. So that you have to develop based on the knowledge of the process. So we call sometimes if then linguistic rules. And then we should have inference mechanism and inference mechanism and a pacification mechanism and also a depacification mechanism. It's important to have all of these the mechanism in place in a correct way. So then so once we combine them, so okay, so fuzzy rules, then we get the inference stage and then we pacify them and then we depacify them as well. Okay, so the based on that we can control the plant once we have the correct inputs. So this is the basic arrangement. Now, please look at some of the textbooks if you want to know more about these stages. It's not that complicated at all. Right. So then the inference mechanism is one of the most important the tasks in Fuzzylogic control. So then how we going to once we have the rule base, so then we have three major inference methods available in the literature. So Mamdani method, Sugeno method, and the Taksumoto method. So these are the three main methods. Of these three methods, so first two are quite popular, and then these are some of the publications that you can find out some of the information related to these technologies. Okay, so the first two methods are important. So in our case, actually, we prefer using Mamdani method, which is the most commonly used method in practice. Okay, so again, if you look at the challenges for Fuzzylogic control, again, as I said, so when you develop, especially the rule base, you should have some in-depth knowledge related to the process. So you have to define the rule base exactly to cover each and every possible scenario of your processing envelope. So that is important. And then so then it is not certain that controller can cover all the situations due to some disturbances or parameter variations or noises. So then it's a challenging task to define your rule base to cover all of these possible scenarios. And then it might be difficult to estimate the membership functions. So then I'll look briefly. I hope you have some idea about those things. And also there are a number of ways of defining fuzzy rules, combining rules, depacifying outputs. So therefore, sometimes it might be difficult for you to just decide which method is the most suitable for a given applications. Okay, so then sometimes the shape of the membership functions is also difficult to decide. So there are a number of possible availabilities. Possibly once you have experience, so then you know, okay, for this type of process or this type of application, so this is the most suitable the type of shape. Right. So then that's about the fuzzy logic if you don't know the process. Right. Here also I would like to briefly go into a case study. So that we recently proposed developing fuzzy logic based control for polymer extrusion. Right. So I just briefly discuss about the extrusion process before. If you know about if you know the extrusion process right now, if you look at the process control in extrusion process, a typical single screw extruder or twin screw extruder, the main extrusion control is based on the PID controllers, traditional PID controllers. What they are doing actually, so they are controlling the screw speed at a set value and also set temperatures at a set value. So that is the main control the ability in the current industry has for extrusion processes. So these PID controllers they keep an eye on the set values of screw speed and then the set temperatures of the barrel and die. So then those are the actual control. They are not looking at any of the process parameters or melt quality parameters or anything to make the control decisions. If you set up a screw speed for certain value, and then the controller will look at the screw speed, whether it is in the certain value or it is just deviating. So then if it is deviating, PID kicks back and then get it back to the normal value. But where the controller doesn't know what is going to happen to the output or the melt, there is no indication. It is not intelligent. So that is why we were thinking about, so why we can't this process make a bit more intelligent? So for like now we have artificial intelligence, neural nets, fuzzy logic, and so many other techniques. So here we thought, okay, so we will try using some fuzzy logic to introduce some rule base for a given extrusion process. So that is what our idea was. So this is the control mechanism that we proposed actually based on fuzzy logic. So again, as I said, because we don't have much time, so then you can look at this publication. I have provided detailed the information about how to develop this. So here, so we just combine the two fuzzy logic controllers, and then we define the rule base for each of them. And then, so we define three reference settings. So that is the melt temperature settings, and then this is we define the maximum allowable temperature variation. So if you remember, I mentioned before that melt temperature fluctuations can go even up to 50 degrees or even up to 70 degrees in some occasions across a 38 millimeter the circular cross section. So it can be that big. So therefore, we can define the maximum allowable temperature variation across the melt flow and the average melt temperature required and also required output of the process. So these are the key parameters. Okay, those are the reference point. And then, so then we, based on that, we can get error signal generated if the process is deviating outside of these values. And here, so we use these two fuzzy logic controllers. At the same time, we are using the proposed sub-sensor in the previous stage. So this sub-sensor is can predict or estimate the melt temperature profile across the melt flow. So then it is a kind of indication that this control is going to get some idea about the actual melt. So that is why we thought, okay, this is a bit more intelligent, and it is going to look at some of the quality, at least the melt temperature profile across the melt flow to make the control decision. Okay, so that is the idea over here. So this is the sub sensor, and then we integrate this sub sensor with fuzzy logic controllers, and we define a fuzzy logic based control system to manipulate screw speed and set temperatures to maintain the reference or to maintain the process within the reference the range. Right. So for our case, so we define the 30 fuzzy rules, and then we use the Mamdani inference method to defuzzify them, as the inference method. And then they were fussified by using triangular shape membership functions because we thought it is the best. And then we tested the other techniques, and then this was the best shape that we could get good performance. And then the range of each universe of discourse was defined based on the experimental information. And then, so these are the outputs here. So this is the input of the fuzzy logic controller. This is related to the temperature variation. And you can see triangular shape membership function, and these are the for melt temperature, average melt temperature. And then, so this is for the input variable, this process output or the mass throughput of the process. And then as the output, what we are trying to do, we're trying to control the screw speed to maintain the process within the required limits. Okay, so then that's all I'm going to discuss about that course. It's because of the time that we have. And then here we have some of the simulation results. So this blue line is the average melt temperature measured with Fuzzylogic. The dot line, red dot line, is without Fuzzylogic, and then the green line is the set value. So this is at 50 RPM. You could see now you don't see much difference here, but okay, if you look at these high speeds now, the high speeds are like as the process speed goes up, the fluctuations are increasing. You could see now the temperature variations here actually. The average temperature is the with Fuzzylogic is green, and the red dot line is without Fuzzylogic. You can see now here temperature variations are lower with Fuzzylogic than without Fuzzylogic. Okay, so this actual variation. So this is the method without Fuzzylogic, and this is with Fuzzylogic controller. Okay, so this is 50 RPM, this is 70 RPM. And then after that, we introduce some disturbances to the process. So here we have introduced 20 RPM disturbance to the input, the screw speed, and then the controller can respond to that. And then also when we remove the disturbance, it can kick back to the normal process, and is trying to get back to the normal process, normal operating conditions. So this is at this is with 20 RPM step change. And here we introduce disturbance by introducing a step change to the third barrel set temperature, and still the process come back to the normal operation. So with that, without just the becoming unstable. Okay, so then with that, we can recognize that as Fuzzylogic is being used for several other processes, we can introduce Fuzzylogic based control for polymer extrusion process as well. So this is really recommended. And also using this new Fuzzylogic control, we can minimize the melt temperature variation across the melt flow. As I said, this temperature could be even 70 degrees, but some of the industrial processes they measure only 5 degrees variation, but actual variation is as big as 50 degrees. So therefore, the new control should be important. So Fuzzylogic or neural nets or AI techniques should be really useful in that aspects, right? So the future works, what we're going to do, we're going to implement this Fuzzylogic based controller in an industrial extruder. So we are still doing that task. Although this process is highly complex, we can write some good fuzzy rules if you understand the process in behavior. Okay, and then also we want to look at some other techniques like neural networks or the other AI techniques in polymer extrusion process control. So as I said, so the SOP sensing, and okay, to wrap up my talk today, so I think that SOP sensing is really important for continuous process, especially. So when we have some troubles of using physical sensors, or when we cannot use physical sensors. So it's really important to do more research on SOP sensing applications for continuous processes which are operating 24/7. And also Fuzzylogic based control are heavily used in nowadays in industry, but for some processes, we don't use this at all. So they are not developed with the technology. So for example, polymer extrusion that I discussed today. So therefore, using these techniques are really important to optimize the processes and also to save energy at the end of the day, to compatible with the circular economy concept in the world, and also to help saving energy to tackle the some issues like global warming, and then to save the planet at the end of the day by reducing the carbon footprint. So so that's all with of my talk today. So with that, I would like to wrap up my presentation, and then from here onward, I would like to take any questions if you have. So again, thank you very much for the organization to inviting me for this talk. I hope you will enjoy the rest of the keynote speeches and also rest of the talks throughout this conference. So wish you all to have the nice time in this virtual conference. Thank you very much indeed.